Okay, in this video we are going to take a look at an interesting construct made out of dipoles, electric dipoles, called the electric dipole layers, and these can be generated in several real life examples, such as a collection of polar molecules which carry a certain dipole moment that are trapped at an air water interface. And this an example of the polar molecules that would show this kind of a structure could be cholesterol molecules or lipid molecules at an air water interface. And so that is what we are going to look at. Essentially a mathematical treatment of it using the concept of dipole layers, where you have a certain polarization spread over a given area. So we assume that the dipole moment of each molecule be P equal to Q times B. Q is the charge, B is the length of the molecule, Q is the effective charge. And we also assume that the molecule occupies an area of S on the interface, and so what we can do is for each drop of the molecules we can assume a uniform electric dipole moment, which will be now tau, and that would be obtained by P divided by S, where S is a scalar. QB over S is going to give you sigma B, and we can model it as a dipole layer that I'm going to draw here, which has a positive surface charge density sigma on the top layer, negative surface charge density minus sigma on the bottom layer, with the dipole moment direction being sigma B, where B is now the distance between the two layers. So that's sort of a model for these two oppositely charged surfaces. And you can start to see this resembles a capacitor. And we will see a lot of similarities between the potential of a capacitor versus the potential of this dipole layer. And in general, the limit that we're going to assume is the macroscopic limit we're going to have b going to 0, sigma going to infinity with the dipole moment density given by tau equal to sigma b, that will be held constant. Okay, so that is sort of our definition of the dipole layer. Now we are ready to find the potential of the dipole layer. So let's take a look at that. And the calculation that we have done in the past of the potential of a point dipole will be useful for us in this calculation, because this one is slightly bit more involved. We also want to generalize, so the first step we need to do is generalize the tau, which was given by sigma times b, into a situation where you may have a non-uniform and oriented not necessarily perpendicular to the surface orientation of the dipole. So it's neither uniform nor oriented perpendicular, and in that case what we will have to do is the tau would be defined as the derivative of p with respect to s. So this is just a generalization of that dipole moment. So now let's recall so when I recall something, I'm going to use a different color, so that way you know this is something you have seen before. And recall the potential of a point dipole is given by phi of r is equal to negative 1 over 4 pi epsilon 0, the dipole moment, and gradient of 1 over r minus r0. And what we are going to do now is we are going to assume that this the dipole layer that we have is a collection of several of these point dipoles, and so then the potential, therefore potential of a dipole layer is the superposition of the potentials of several infinitesimal infinitesimal dipoles on the surface. And so with that assumption, then we're going to get phi of r as -1 over 4 pi epsilon 0 integral over the surface of, now the small dipole moment is dp at the position of rs, and then you have the gradient of 1 over r minus rs. Rs is the source point, the point where the potential is located. And so what we need to do now is write it down in terms of the dipole moment per unit area. And so it is still the surface integral. We have surface integral, and instead of dp we have now surface integral times tau rs dotted with gradient of 1 over r minus rs. And so it is useful to interpret this result in terms of the charge density, and that gives us kind of a physical picture of what is going on. And so what we do is, so the goal here is identify the charge density causing this potential, and we call it rho L, let's say, for the charge density of the layer. And so what we can do is we are going to write down the surface integral and translate that into a volume integral. And in that process we need to realize that the dipole layer is situated. So that's our first input. The second input is going to be that the dipole layer coincides with z equal to 0, and to realize this special connection with z equal to 0, the surface points are going to be only along the x direction and y direction, and the source vector r is going to be rs prime plus z prime z hat. And so with this information we are in a position to rewrite the potential, which would now look like 1 over 4 pi epsilon 0 the volume integral d cube r prime, because we have now we are essentially looking at the surface integral, but d cube r prime delta z prime would bring us back to the surface, and the r prime vector for the point on the surface is just rs prime dotted with gradient 1 over r minus rs prime. And so that part hasn't changed. What we need to do really is not write down s anymore, because we have now a volume integral. This r s prime now has to be replaced by rs. So that's a new change here that you need to recognize. And what we now do is integrate by parts this expression, and then move the gradient operator r to gradient operator over the coordinates r prime. So with that change, and it's a trivial change, you can see that the derivative now, instead of applying to r over r minus term, it's going to apply to the r prime coordinate, and so it's going to apply to that term. And so it's very easy to see the effect of the integration by parts. And we are going to get the first term in after the integration by part, of course, will go to 0, because the 1 over r minus r prime, this whole product of the terms is going to be negligible at the boundaries, and so we don't have to worry about that part. All that is left now is the del prime operator applied on the product of the tau and the delta function, because they are both functions of the prime coordinates, and the derivative now is applied to the prime coordinates. The denominator stays the same, so there is no change there. And so what we need to do now is again recall the potential of a charge density rho of r prime, let's say, and so it's given by rho of 5r as 1 over 4 pi epsilon 0 integral d cube r prime rho of r prime over r minus r prime. And so by comparing this with the expression that we found, we get the charge density of the layer rho of r as negative divergence of the tau of rs delta of c. And so I think I need to change this, rewrite it again. Give me just a second here. We're going to write it. So this implies that the charge density of a dipole layer is going to be rho L of r is going to be negative gradient of tau rs multiplied by delta of c. And so that completes the discussion of the dipole layer potential. We still need to interpret this and connect it with the capacitor potential, but we will work on